Yeah, thank you, and especially thank you to the organizers for the invitation and giving me the opportunity to talk here. So I want to talk about recent work with Brand Jones that we put on the archive. And I should say Brand is actually on the job market this year, so just in case you want to hire him. So I want to talk about affine crystals for type E6. So I give you a theorem for these crystals for type E6, and I also will give you a conjecture for E7. And I will explain to you why the conjecture is a conjecture and not a theorem. But so let me first outline the aim of my talk, and then like Sasha did it in his talk, after 5 minutes you basically know the whole story of the talk, and then I just fill in the details. Okay, so what the aim is really the construction of Kirillov-Reshetikhin crystals for type E6. So Kirillov-Reshetikhin I will always abbreviate by Kr. So of Kr crystals of type E6, or I should say affine E6. And when we talk about Kirillov-Reshetikhin crystals, they are usually indexed by two parameters, by an R and an S. So the S is usually just a positive integer, and the R usually corresponds to a node of the Dinking diagram, and I will only do this in fact for R equal to 1, 6, and 2. So I've drawn my convention for the labeling of the Dinking diagram. So this is node 1, node 6, and node 2. And I should say that the node 2 actually corresponds to the adjoint node, and there is actually work by Bankert et al., and they constructed the level 1 crystals in a uniform fashion, so for all types, for the adjoint node. But this was all for level 1, so I'm actually doing this now for type E6, but all possible S, so all possible levels. And there's, of course, also the seminal work by Kang, Kashiwara, Misra, Miwa, et al. And Nakashima, Nakayashiki, where they constructed perfect crystals for a lot of cases. And recently with Okado and Ghislaine Fourier, we actually constructed all BRS for the non-exceptional types. So the exceptional types are still some that are left in general. Okay, and so we do this for type E6, and then, as I said, I will also give a conjecture for E7 for the adjoint node. And so my labeling for E7 is this, and the adjoint node in this case is the 1. Okay. So let me tell you what our methods will be. So the method is that we are going to use the classical decomposition of these Kirillov-Reshetikhin crystals that were given by Chari. So we know that the classical decomposition in the cases that we are interested in are given as follows. So BRS is in fact as a classical crystal. So by this I mean I'm going to remove the zero arrow, the zero node. It's isomorphic to BS lambda R. And by lambda R I mean the fundamental weight, the R's fundamental weight. And this is true when R is equal to 1 or 6 in my labeling. And so I said I'm also going to do the adjoint node. So B2S, in fact, is isomorphic to a direct sum, K0 to S, BK lambda 2. So these crystals, as classical crystals, they are they're connected, and here you actually have a direct decomposition of crystals. Okay, so that's what we start with. So we know this, and therefore we know all the classical errors already. So basically what we need to do is just, if we want to give a combinatorial description of these crystals, we need to say what the F0 is doing. And that we are going to do by using a promotion operator. So I'm calling this a promotion operator, but perhaps I should call this like a Dinking diagram automorphism, but acting on the level of crystals. So here I should say Chari. So we are, in fact, if you look at the Dinking diagram for type E6, there are several Dinking diagram automorphisms. So you can flip along this side, but there's also this Dinking diagram automorphisms of order 3. So when you map the 6 to the 0 to the 1 to the 6, and the 5 to the 2, and the 4 to itself. And in fact, it's going to be this Dinking diagram automorphism that I'm going to use. And as you can see, for E7, we only have a Dinking diagram automorphism of order 2. And in the proof that I'm going to give, it's important that we actually have something of order 3. That makes the proofs a lot simpler, and that's why what we have is only a conjecture for E7. But in principle, there's no abstraction. It's just it's a lot more work to do. Okay, so we are using the automorphism of order 3. Okay, so that's basically the summary of my talk, and you can go to sleep now if you want. And what I'm going to do is now I'm going to fill in the details. So I'm first going to tell you a little bit, since we are starting with this, I need to tell you a little bit about how these crystals actually look like, these classical crystals. So for classical types, there's this tableau model of Kashiwara Nakashima. And basically what I need to tell you is how to upgrade this to type E6. And then I'm going to tell you how to construct this promotion operator. Okay, so let's start by looking at these things, and that's why I have this transparency there. I hope it's sort of visible. And if not, I mean, it's basically just the structure of the crystal. So that's a crystal B lambda 1 of type E6, and one way of how you can get this is by using the Littleman path model, or actually the way we did it is we did the Leonard-Posnikov model, and you can just construct this crystal, and this is what you get. So you get the arrows, and the way that we labeled our nodes is, if you look at this crystal, every node has arrows coming in and arrows coming out, but they are all strings are of length 1. So the way that you can label your nodes is just by which arrows coming in and which arrows coming out. There's no node that sits somehow in the middle of a string, right? So therefore, for example, this 0 bar 1. So forget about the zeros for the moment. This really means there's just a 1 arrow coming out. This is labeled by 1 bar 3, so 1 arrows coming in and 3 arrows coming out. And this crystal has 27 nodes. Do you have a question? No. This has 27 nodes. And in fact, if you look at B lambda 6, right, so you have the 1 and the 6, the B lambda 6 is precisely the dual of this crystal. So instead of reading it this way, with all arrows this way, you would start down here and you reverse all the arrows, and then you would go up. That's the B lambda 6. So B lambda 6 is dual to B lambda 1. Okay? And now we also want, of course, the B's for all other fundamental weights. So the lambda 2, the lambda 3, and so on. And you can get them all by construction from this crystal, in fact. So as I said, B lambda 6 is dual to B lambda 1, and then B lambda 2 we can actually get by embedding into B lambda 6 tensor B lambda 1. So this is similar to the Kashiwara-Nakashima construction of Tableau, where when you have a column, you basically embed this into a tensor product. And I should warn you that I'm always using the opposite of Kashiwara's convention for the tensor product. Okay, and the way that this guy sits in here, it's generated by the element 2 1 bar tensor 1. So the 1 is basically here this highest weight element, and then the 2 bar 1 is this guy here at the corner. If you tensor them, you actually get the B lambda 2. And then similarly, B lambda 3 you get by taking 1 bar 3 tensor 1, and this sits in B lambda 1 squared. And then B lambda 4 you can get by looking at B lambda 1 cube, and the element that generates this is 3 bar 4 tensor 1 bar 3 tensor 1. And then finally the B lambda 5 sits in B lambda 6 squared, and that's generated by 6 tensor 5 bar 6. Yes. Yes. And there are different ways to actually realize these.
So the last one, 5 to 6 about.
Yeah. Yes. Yes, thank you. Okay. So now we have the realization of all the fundamental weights. And then if you follow what Kashiwara-Nakashima did, so this basically now is the analog of saying what a column is in the usual way of doing Tableau. And then if you have a general weight lambda, dominant weight lambda, so lambda is a sum of lambda, some fundamental weights, then in the Kashiwara-Nakashima model you put those columns next to each other, and then you have conditions on the columns. And if you think about type A, basically what you get is that things are weakly increasing. And for other types, you get more complicated conditions, there are extra conditions, but the main idea is that things are weakly increasing along rows. So now what I want to do is I want to basically define some analog of this. So let me give you first a definition. So if you have some dominant weights, let me call them, and you can think of them as fundamental weights if you want, then I'm going to say that B1 tensor Bk in the tensor product is pairwise weakly increasing if the following is true, namely if you take every consecutive pair, so every Bj tensor Bj plus 1, you want that those live in the B of the sum of the two things. So this should be B mu j plus 1. And that, of course, sits inside this So I'm thinking of this as living inside of B mu j tensor B mu j plus 1. Okay. And actually, I can probably get rid of this now, then I have a little bit more space. Okay, so this crystal is really generated by, so if I think of it in terms of the tensor product, I can take the highest weight vector of this guy and the highest weight vector of this guy and take the tensor product, and then this one is just generated by that. And so saying that some pair sits in here just means it's connected by F's with this highest weight element. Okay, and in fact we have also explicit descriptions in certain cases. So for example, if you, so this is in E6, if you want to know whether B1 tensor B2 is in B2 lambda 1, so which sits in B lambda 1 squared, then this is true if and only if B2 can be obtained from B1 by a sequence of F. So I'm going to write this now as F vector B1. So if you think of this graph that I just had up there just as a poset, what this means is it's a poset and these are actually comparable to each other, and the B2 is in fact greater than the B1. So B1 greater or equal to B2 in the B1 poset. Yes?
How is this to tell whether you're in B lambda 1?
That was this graph that I just set up there.
You have to remember that information, whether you're on that.
Yeah, I mean, so the way I'm constructing this, I have to remember this graph, these 27 nodes, and then everything else you have to, well, you have to, construct in this way. Okay, and then, for example, another explicit condition, since we are going to look at B2S, it might be interesting to know when is an element in B2 lambda 2. So remember B2 lambda 2 I can realize as a tensor product of B lambda 6 and B lambda 1. So I'm going to write two things. So this is in B2 lambda 2 if and only if. So I'm now going to write this notation as saying that we have something in this poset. So this is if B2 is greater or equal to B1 in the poset, C2 is greater or equal to C1 in this so this is in the B1 poset, this is in the B6 poset. And then if there's an extra condition, if in fact C1 is dual to B2, right, so this guy lives in B1 and this guy lives in B6, so they could in principle be dual to each other. Then there's an extra condition, namely then we want that this whole thing is strictly greater than B2 tensor B C2. So by this I mean there's an F string that takes you from here to here. Okay. So these are just some special cases that we worked out, and there's another little lemma which says the following. So let's suppose lambda I1, lambda I2, they're distinct fundamental weights. And let's suppose that k is equal to k1 plus k2, and k1, k2 are non-negative integers, then B1 up to this tensor product BK is in fact an element of K1 lambda I1 plus K2 lambda I2. So it sits in here if and only if. So this guy here is pairwise weakly increasing. Okay, so this is really the analog of the Kashiwara-Nakashima condition. But I should warn you that this is in fact not true anymore if you take, for example, 3 different weights. So if you think about type A, this would be a tableau where you have 3 different column heights, right? Because every lambda I corresponds to a column of height I. So if you had 3 different column heights in your tableau, then in type E6 this would not be true anymore. And let me give you a counterexample. So this lemma does not generalize to 3 or more weights. Yes?
I thought there's a way to always tell if you have a pair or some tensor product, how to tell when you're in sort of that leading connected component that you're trying to, that condition you're trying to detect. I thought there was some sort of condition that you could always tell whether that was happening or not.
Well, I mean, in general, I think you would have to see, you would have to go up to the highest weight vector and then see whether it's
something like you have for each pair of consecutive factors, you have sort of some sort of biggest stem zero that you could be in on one factor and sort of the smallest one you can in the other factor, and they have those two. There has to be some sort of comparability between those two elements.
Yeah, I think this is just an explicit condition for.
No, it's not, because that's not dealing with extremal weights. You're just any weight there. I mean, you're anywhere in the crystal, so that's not equivalent.
So you only want to look at the extremal weight vectors?
Yeah, I mean, it comes from standard binomial theory. I think Lakshmi had some sort of condition.
Okay. But this is only for 2 things, or in general?
Just any sequence of things that the conditions on successive elements in tensor effect.
Okay. But anyway, this particular lemma definitely does not go through if we put 3 different things in there. And as an example, take, for example, 2 bar 5 tensor U6 tensor U2. So by the U's, I mean the highest weight vector in the corresponding crystal of the fundamental weight. So this is an element in B lambda 1, tensor B lambda 6, tensor B lambda 2. Right, so you can check that every pair here is in fact weakly increasing, so that's trivial. And you can check that, so I mean this guy has only a 6 coming out, and you can check that you don't need any E6 to go to the highest weight vector, so this is in fact in the component U1, U6. But this is a highest weight vector, and it's not U1 tensor U6 tensor U2. So this does not live in B of the sum of these things. Okay, So, so this is not and b lambda 1 plus b lambda 6 plus. But you can in fact give an equivalent state, or I mean a generalization of this lemma for arbitrary lambdas, and the way that we did this is, I don't want to give the details, but you can apply some omegas, so you define some isomorphisms between crystals similar to the R matrix, but we are in the finite case, so not in the affine case, where you swap tensor factors, and then you require that if you apply these isomorphisms, then you always have a weak increase for any of these. Okay, so you can do something like this, but I don't want to give the details. Okay, so this basically now takes care of the classical part. Remember, when I gave my outline, I said that we said that our BRS is isomorphic to some direct sum of classical crystals, and this now describes all of this. And the way that we are going to construct our affine crystal is by now defining some promotion operator. And I now want to give you the definition of what I mean by a promotion operator, and then define this promotion operator for you for E6. Okay, so let me first define what I mean by a promotion operator. So let me denote by C tilde an affine linking diagram. And this has an index set associated to this that I'm going to call I tilde. And then if we remove the zero node, then you have an underlying classical linking diagram. So I'm going to denote this by C, and the corresponding index set is I. So I tilde is I union 0. And so let me call P dot an automorphism of C tilde. So in our case, when we talk about the E6, I really mean this order 3 linking diagram automorphism. And let's suppose that B is a classical crystal of type C. Okay, that's basically the setup that we have. And then we say that this P dot induces a promotion or perhaps you could say a twisted isomorphism if there exists some bijection, and which I'm going to call P. So that's induced by this P dot, which goes from the classical crystal union boldface 0 to B union boldface 0. So this is really, so when you take an element in your crystal and you hit it with an Fi, sometimes you can annihilate it, and this is basically what happens when you annihilate it. That's what the 0 stands for. Such that the following is true. Namely, we want that PB is equal to this boldface 0 if and only if B is equal to the boldface 0. And then under this P, the Fi's behave as follows. Namely, we get here Fp dot I of B. Of P of B. And then similarly for the EI. Okay, and we want this to be true for every element in our classical crystal and for every I in I, but such that my P dot I is not equal to 0, because in that case we don't know what the EI or FI actually is. So for all of these, such that P, I guess P of, I guess I want this, like this. Okay, and then we say that, so once you have something like this, then in fact you can define an affine crystal. So given a promotion, one can define an affine crystal by saying that, okay, my F0 should really be P inverse Pi, P dot of 0, sorry, P. Okay. So that would define for you an affine crystal, but what you really want from such a crystal, if you just think of it as a combinatorial crystal, you want this to be a regular crystal. So by regular, I mean if you remove any of the nodes, you should actually get a classical crystal from this. Okay, so let me write this as a definition. So if you have B a classical crystal, and if I now denote by B tilde the corresponding affine crystal, so by which I mean it has the same nodes as this, it has the same classical arrows, and it has some zero arrows possibly constructed like this, then if B tilde is regular, then I call this a combinatorial affine crystal. That's just a definition. So now what I want to prove for you, since as we heard every talk is supposed to have at least one proof, that if we start with such a promotion operator of order 3, so if we have a promotion of order 3, then this, by this construction, will define for us a regular combinatorial crystal. Okay, so that's a theorem. So be a classical crystal of type E6, and suppose that there exists a promotion B from P from B to B of order 3, then my claim is that then the corresponding affine crystal is in fact regular, or is a combinatorial affine crystal. So how can we see this? Yes?
Can you remind me of your definition of regular?
So regular means if you remove any of the nodes, the underlying crystal should be a classical crystal.
So does this imply that it's the crystal of an actual representation?
Yeah, in particular, yeah. I mean, well, I mean the ones once you remove the nodes, not necessarily the one, not
necessarily the crystal of an affine representation.
No, this one, that's why I call it a combinatorial affine crystal. Right. But the one, once you remove the node, that will correspond to a real crystal, yes. Okay, but to prove that this is regular, so what we need to show is, so let's remind ourselves how the dinking diagram looks like. So this was 1, 3, 4, 5, 6, 2, 0. Right, so we already know, since we are starting with a classical crystal, if we remove the 0, everything is fine by construction. So we only need to show that if we take an F0 and any other Fi, that we have the correct commutation relations between the Fs. And now we can in fact use the fact that P has order 3. So if we take any F0 with an Fi, as long as I is not equal to 6, because remember 6 will be mapped to 0, then we can use that this is in fact equal to P inverse F1P and then P inverse F P dot I P, and then these things cancel out. And then if I was not equal to 6, this is not 0, this thing. And then since F1 and whatever Fj you have, I mean, is in fact comes from a classical crystal, the commutation relations are fine. Okay, so this is if I is not equal to 6. But if I is equal to 6, what we can do is we can just use we can just take the P in the other direction, since we have something of order 3. So for 6, we are just going to use that this is equal to Pf6, P inverse, Pf1, P inverse, and then again these things cancel out, and we know F1 and F6 commute, and therefore this is also equal to F6, F0. Okay, but what we really used here is that our P is of order 3. So the thing that the node that gets mapped to the 0 node, I had to do something special. For that one, I actually had to take like the P inverse. And if you have something of order 2, then if you think about our E7, the 0 node sits here. And then if you use this dinking diagram automorphism, the 0 gets mapped to the 7. And then you don't automatically know that what you get is a regular crystal. So you actually have to check this by different means, not by these very simple arguments. Okay. So now let me give you the explicit description for these P's. So basically what I'm now going to do is I'm going to give you the explicit description for the P's, and all we need to do is check that our P actually has order 3, and then we automatically know by the theorem that what we get is regular, and then by some uniqueness statements we can actually check that what we get is in fact a Kirillov-Reshetikhin crystal. So let me first look at BRS when R is equal to 1 or 6. So then by Chari we know that BRS, as I already said, is isomorphic to B as lambda R. And it's pretty easy to prove that if you look at the I minus 1 highest weight nodes, highest weight vectors in B as lambda R, they're completely determined by weight. And therefore, one can now define a twisted or promotion operator, twisted isomorphism or promotion operator P, which goes from B S lambda r to B S lambda r with p cube equal to the identity and doing the correct things on the weights. So mapping precisely the weights where they're supposed to go under this p dot. Okay, so what one just has to check is that the p cube, that p is really of order 3. And the reason why I'm only looking at I minus 1 highest weight vectors is because my p really maps, if you look at the Dinking diagram again, the 0 gets mapped to the 1. So once you apply your p, you don't know anymore what the thing did before. And then, in fact, to prove that, so this now defines for us a combinatorial affine crystal, and then you still have to check that this is in fact the Kirillov-Reshetikhin crystal, and that we just did by proving a uniqueness theorem. So let me not go into further detail, but this is really the corresponding Kirillov-Reshetikhin crystal. So now if we want to look at B2S, so the one for the adjoint node, then again by Chari we know that B2S is isomorphic to this direct sum of BK lambda 2. And now what we want to do is we want to again kind of say what these I minus 1 highest weight vectors are going to look like. And they are in fact in bijection with certain combinatorial sets. So let me define CM, just the set of triples L2, L3, L5. So they are basically just compositions of M. So we want that L2 plus L3 plus L5 is equal to M. And the reason why I'm writing this way is because these will turn out to be the coefficients of the weight lambda 2, lambda 3, lambda 5. And then we have a proposition which says that there exists a bijection between the I minus 6 highest weight nodes of BK lambda 2 and the union M from 0 to K with a set CM. And similarly, you have the same for I minus 1 highest weight nodes. And I should say, so an element B will be mapped to a triple L2, L3, L5. And the weight, the I minus 6 weight of this B is in fact equal to L2 lambda 2 plus L3 lambda 3 plus L5 lambda 5. And the component K where it sits in is actually also completely specified. Namely, that is given by this weight and the phi6 vector, like the phi6 string of the crystal. So K is equal to phi6 of B plus L2 plus L3 plus L5. And since we have this nice bijection, and I should say we have precisely the same bijection when we take I minus 1 highest weight vectors, and we have the same kind of bijection, but the K will then be here a phi1 of B plus these L's. Okay, and using this, we can now define a promotion operator. Namely, we can say that there exists a unique twisted or promotion operator P from bk lambda 2 to the sum bk lambda 2 which has that p cube is equal to the identity. So if you don't require this, then there are in fact several, but if you require this, then there's only one. And it does the correct things on weights. And I should also say that if you map an element from a component k here to a component k prime, then we know what it does to the component. So the k prime, where it lands in over there, is in fact equal to s minus k plus the 2 weight of the b plus the 3 weight of the b plus the 5 weight of the b. So perhaps I should demonstrate this in terms of a picture. So if you take, for example, b to 3, so s is equal to 3, then our k could be equal to 0, 1, 2, or 3, right? These could be our components. And then we saw associated to these components, we have these sets C that label for us our highest weight vectors. So for each of these, you have the set C0. But for this one, you also have the set C1. And then here you have C2. And here you have C3. And then what our promotion operator does, it maps the elements in here to them, well, not quite to themselves, because they go to, I mean, instead of going to I minus 1 highest weight vectors, you go to I minus 6 highest weight vectors, but the labeling set is still the same. So these get mapped to each other, these get mapped to each other, this gets mapped like this, and then finally this gets mapped like this. Right, so you basically reflect somehow according to these sets. And then again, by a theorem of Kashiwara, Misra, Okado, and Yamada of 2007, they showed that if there is a combinatorial, or if there is an affine structure, a regular affine structure, which has this classical decomposition, then it is equal to the Kirillov-Reshetikhin crystal. And therefore, since we have this, this has to be the Kirillov-Reshetikhin crystal. Okay, so now I'm basically out of time. So I just wanted to say, so we have this conjecture also for E7. And if you want, I also have, this is all encoded in Sage, which is some open source computer software program. So if you want, I can show this to you, or you can just come to me after the lecture and I can show you how this works. Thank you.
In this proof that you gave with this affine crystal